Have you ever thought about how amazing it'd be to see the invisible world inside a cell?
Oh, yeah.
Like pinpointing a single protein out of millions?
It is pretty wild. It's like trying to find a needle in a haystack, but on a microscopic level.
Yeah, exactly.
Luckily, we have a tool that gives us that kind of superpower fluorescence microscopy.
Oh, wow. Yeah.
It's how we can actually observe those intricate dances of molecules within living cells.
Fluorescence microscopy.
Yeah.
How does that even work?
Well, it all starts with these special molecules called fluorophores.
Okay.
They're like tiny light bulbs
Okay.
that can absorb light and then re-emit it at a different color,
Oh.
creating their own little light show.
So they're like nano-sized disco balls inside our cells.
Haha, that's a great way to put it.
Yeah.
But the real magic is in something called the Stokes shift.
Oh, okay.
It's the difference between the color they absorb and the color they emit.
Okay.
And this shift is crucial because it helps us distinguish the fluorescent signal from all the background noise.
Oh, that makes sense.
Yeah.
So it's kind of like you can pick out a specific firefly in a field full of flashing lights because of its unique blinking pattern.
Exactly.
Okay.
Yeah.
But how do we make sure we're only looking at the light from the fluorophores
Right.
and not getting confused by all the other light in the cell?
That's where the microscope's filters come in.
Okay.
They act like bouncers at an exclusive club,
Okay.
only letting in the specific wavelengths of light that we want to see.
So we're basically cherry picking the colors of light that give us the information we need.
Absolutely.
Clever.
And the whole process is governed by the laws of quantum mechanics,
Wow.
which adds another layer of complexity.
Okay.
You see, a fluorophores lifetime, so how long it stays excited,
Right.
and its quantum yield, how efficiently it emits light,
Okay.
determine how bright and long-lasting its glow will be.
So we're dealing with some pretty fundamental physics here.
Yeah.
But how does this all translate into building a microscope that can actually capture these tiny flashes of light?
Good question.
Yeah.
It's a bit more complicated than your typical light bulb and magnifying glass setup.
Okay.
We need specialized light sources like lasers
Oh.
to excite the fluorophores.
Okay.
And then there's the objective lens, which not only magnifies the image, but also plays a critical role in focusing both the excitation and emission light.
So the lens acts like a two-way street for the light,
Exactly.
ensuring it hits the fluorophores and then captures the emitted light.
Yeah. And finally, we need highly sensitive detectors like photomultiplier tubes
Okay.
to pick up that faint fluorescence signal and turn it into an image we can actually see.
Okay.
So these detectors amplify the signal, allowing us to visualize even the faintest glow from those tiny fluorophores.
Wow.
Yeah.
It's incredible how all these components work together to reveal a hidden world that was once invisible to us.
It really is amazing.
Yeah. It makes me think about the fluorophore lifetime.
Oh, yeah.
Are there limitations on how long we can observe these cellular processes?
Yeah, that's a great question.
Yeah.
And it highlights a challenge that researchers often face.
Oh,
It's like a ticking clock.
Right.
You have to capture your images quickly before that signal fades away.
So it's a race against time to capture these molecular events.
Exactly.
Yeah.
But scientists are always pushing those boundaries.
Right.
There are even more advanced types of fluorescence microscopy that overcome some of these limitations and allow us to see even more.
Oh, wow. Okay, so more advanced. Like what? This is already sounding pretty high tech.
Right. One of the most powerful techniques is confocal microscopy.
Okay.
Imagine being able to slice a loaf of bread
Okay.
and see all the details inside each slice.
Okay, so instead of seeing the whole cell at once, you could look at it layer by layer.
Precisely.
Yeah.
Confocal microscopy uses pinholes to create what are called optical sections.
Okay.
These thin slices give us much sharper images and allow us to build 3D models of cells.
Wow. So we can create a 3D map of the cell's interior.
Absolutely.
That's amazing.
Yeah, and then there's multi-photon microscopy. Instead of using one high-energy photon to excite the fluorophore,
Right.
it uses multiple low-energy photons.
Okay.
Think of it like this. Sometimes it's easier to get a few friends to help push a heavy object rather than trying to move it yourself.
So it's like teamwork on a molecular level.
Exactly.
Like that.
And this teamwork allows us to see deeper into tissues without causing damage.
Oh, wow.
Plus, since it uses lower energy light,
Right.
it reduces the risk of photobleaching, that ticking clock we talked about earlier.
Okay, so multi-photon microscopy allows for longer observations and deeper penetration into the sample.
Right.
It's a gentle giant of microscopy.
I like that, a gentle giant.
Yeah.
That's very apt.
Okay, so we've got these incredible microscopes.
Yeah.
But what are they actually used for? What kind of biological secrets can we unlock with them?
Oh, the possibilities are practically endless.
Oh, wow.
For example, by tagging proteins with fluorescent labels, we can track their movements and interactions within the cell.
So it's like putting a GPS tracker on a molecule and watching it go about its daily business.
Exactly.
That's so cool.
We can see them bind to each other, move around to different parts of the cell,
Right.
and even watch them carry out their specific functions.
It's like we have a front row seat to the molecular machinery of life.
I know, it's amazing.
What else can we observe with these techniques?
You can also use specific probes that light up different parts of the cell.
Okay.
For instance, we can illuminate the mitochondria,
Okay.
which are the powerhouses of the cell,
Right.
or the cytoskeleton, which provides the cell's shape and helps it move.
So it's like having a highlighter for different cellular structures.
Exactly.
We can pinpoint the exact location and organization of these crucial components.
And it's so fascinating.
This is also fascinating. I can only imagine the amazing discoveries waiting to be made using fluorescence microscopy. Thinking about these tiny molecules,
Yeah.
like these fluorophores, being like the key to unlocking so many secrets about how cells work. It's like they're whispering stories to us,
Right.
and we just need the right tools to listen.
That's a beautiful way to put it.
Yeah.
It reminds me of how the discovery of the Stokes shift, that difference in color,
Yeah.
was a pivotal moment in the development of fluorescence microscopy.
Oh, wow.
It was like scientists suddenly had a way to decipher the language of these tiny beacons.
Yeah, I can only imagine the excitement when that discovery was made.
Oh, yeah.
Like they stumbled upon a secret code
Hmm.
that unlocked a whole new world of understanding.
Absolutely.
And we've come so far since then.
Yeah.
With even more advanced techniques like confocal and multi-photon microscopy.
Right.
What's next? What does the future of fluorescence microscopy hold?
Well, one area that's really pushing the limits is super resolution microscopy.
Okay.
Think about it. Like traditional light microscopy has a resolution limit,
Right.
meaning we can only see objects down to a certain size.
Okay.
But super resolution techniques are breaking that barrier, allowing us to resolve details that were previously thought to be impossible to see with light.
Wait, so we can actually see things smaller than the wavelength of light?
Yeah.
How is that even possible?
I know it sounds like something out of science fiction.
Yeah.
These techniques use some ingenious tricks,
Okay.
like switching the fluorescence of individual molecules on and off,
Whoa.
or taking advantage of the way they emit light to bypass the diffraction limit.
Okay.
It's like using a special kind of pointillism to create an image with incredible sharpness.
So we're basically taking multiple snapshots of these tiny blinking molecules
Right.
and then using clever algorithms to reconstruct a super sharp image.
Exactly.
That's brilliant.
And the implications are huge.
Okay.
We can now study the organization of proteins within cell membranes,
Wow.
track the movement of single molecules in real time,
Okay.
and even watch how viruses assemble inside cells.
That's amazing.
It's like opening up a whole new dimension of biological exploration.
It's like we're zooming in further and further, revealing more and more detail with each new advancement.
Exactly.
It really makes you wonder what other mysteries are hidden within this microscopic world.
Absolutely. And it's not just about seeing smaller.
Right.
Scientists are also developing new types of fluorescent probes
Right.
that can sense changes in the cellular environment, like pH or calcium levels.
Oh, wow.
This allows us to study how cells respond to stress signals and other changes in their surroundings.
So these probes are like tiny sensors embedded within the cell, reporting back on what's going on inside.
Precisely. It's like having a network of informants within the cell,
Wow.
giving us real-time updates on the state of the cellular environment.
That's so cool.
And these sensors are becoming incredibly sophisticated.
Okay.
Some can even change color in response to specific molecules,
Wow.
allowing us to track the movement of those molecules within the cell.
So it's like having a color-coded map of the cell's internal communication network.
Exactly.
We can see how information flows within this bustling metropolis of molecules.
Yeah.
It's truly remarkable.
It is, and the best part is that it's not just about looking at static images anymore.
Right.
We can now capture movies of cellular processes unfolding in real time.
Oh, wow.
We can see how cells divide, move, communicate,
Okay.
and carry out all the essential functions of life.
It's like having a microscopic documentary playing out right before our eyes.
I know.
We're not just observing the structure, we're witnessing the dynamic processes that make life possible.
It really is amazing.
It's hard to believe that we've come come so far from simply looking at cells under a basic microscope.
I know, it's a testament to human ingenuity and the power of scientific curiosity.
Yeah.
Who knows what incredible discoveries await us as fluorescence microscopy continues to evolve.
Right.
One thing's for sure, we're only just beginning to scratch the surface of what we can learn about the microscopic world within us.
Well, I'm certainly feeling inspired to delve deeper into this fascinating world.
Good.
Thank you so much for guiding us through this deep dive into fluorescence microscopy.
Oh, it was my pleasure.
It's been an illuminating journey.
It's always a joy to share the wonders of the microscopic world.
And to our listeners, thank you for joining us on this exploration. We hope you've gained a new appreciation for the invisible world that surrounds us and the incredible power of light to reveal its secrets.